Okay, thank you. So yes, I was asked to talk about effective strings in QED3, and this will be based on this paper that appeared a few months ago in collaboration with two of my PhD students, Nathaniel Vael and Tal Sheffel. So I'll begin by reviewing the standard story of effective string theory and its predictions. I mean, probably this is not really necessary in this audience, but still I'll do it just for the talk to be complete and to clarify what are the predictions. And then we'll see that there are some classes of theories where the standard effective string theory doesn't work, and in particular, that class includes also QED3. So we'll explain why that happens and see what are the alternative methods that we can use in these cases, and then I'll describe what are the different results that we get in theories, in particular QED3, which differ from the standard effective string theory story. So let's begin with the standard story. So standard effective string theories. So many quantum field theories have string-like excitations. These can be confining strings in pure Young-Mills theories. They can be solitonic strings. They can be domain walls in 2+1 dimensional field theories, or any other types of string-like excitations. And in many cases, these strings are stable or at least long-lived. In some cases, there is a one-form symmetry that they are charged under, and then they're definitely stable. Well, in other cases, they can still be long-lived, like in QCD with very massive quarks. So in this talk, I'll assume that the strings are effectively stable. And we'll also assume that the quantum field theory that we're talking about has a mass gap in the bulk. And then in that context, if we have a string-like excitations and we take the string to be very long, so we take its size to be much larger than the inverse mass gap, then the only light degrees of freedom are the transverse excitations of the string. So if we have a d-dimensional field theory, then the string has d-2 massless scalars on its world sheet, which correspond to its coordinate in the transverse directions, and which are massless because they are Nabu-Goldstone bosons for the translation symmetries that are broken by the strings, and also the Lorentz symmetries that the string breaks. And so these are d-2 massless scalars on the string world sheet. And all the other degrees of freedom are typically at the scale of M gap, or at the scale of, so if the string has a tension T, then there may be other degrees of freedom at the scale of the square root of the string tension. But for energies that are much smaller than both M gap and the square root of the string tension, we can write down an effective field theory for in the presence of this long string that includes only these Nabu-Goldstone bosons and no other degrees of freedom. And the interesting fact that was derived 10 to 15 years ago by many people here is that this effective action is actually universal up to a rather high order in the derivative expansion. So it's convenient, well, one can write this effective action in many ways. I'll write it using the induced metric on the string world sheet. So I write here, I'll call x mu the embedding of this string in space-time, and say sigma and tau can be the world sheet coordinates of the string. Of course, this x mu includes not just these d-2 massless scalars, but also the directions along the world sheet. So this is a somewhat redundant parameterization. But using this metric, it's easy to write down the universal effective action for these degrees of freedom. I mean, so the first term in the effective action is just the Nabu-Goldstone action, namely the tension of the string times the induced area of the world sheet. So this is the standard term that we have in any string theory. And then the interesting fact is that the corrections to this leading term arise at a rather high order in the derivative expansion. So they take the form of some coefficients, and then we have square root g times the curvature of the metric, of this induced metric squared. And then we can have various other higher derivative terms. So in the context of an effective action that we write down for the Nabu-Goldstone bosons, these corrections, these non-universal corrections, start at a derivative order. So they're highly suppressed at low energies. And what this means is that we have universal predictions that are valid in any string theory for all the low energy properties of the theory in the presence of this long string. And in particular, we have universal predictions for the energy levels of long strings. So we can discuss either closed or open strings. For simplicity, I'll take the case where our theory lives on some long circle of circumference L. So if we have then a string that's wrapped on this circle L, then the universal predictions for the energy levels are that the energies of the long strings are given by the result from the Navier-Stokes action, which takes the following famous form. Let's do over 24. So this is the standard formula that's familiar from string theory. And then the corrections to this formula, if we're in 3 dimensions, or if we're talking about the ground state, then they start at order 1 over L to the 7th. So for d equals 3, the corrections to all the energy levels are given by this formula, and then these deviations from this formula start at order 1 over L to the 7th. While in dimensions higher than 3 for the excited states, then there are some universal corrections that start already at order 1 over L to the 5th, and that it won't write down because they won't be imported here. And then there are non-universal corrections that also start at order 1 over L to the 7th. So this is one completely universal predictions that hold for any theory of a string where we have a mass gap and we're talking about energies much smaller than the gap and the scale of the string tension. Another universal property is the width of long strings. And now I'll talk about, say, long open strings. So let's imagine that we have some long open string of length r. And in that sense, suppose that its ends are just held fixed, but the string still fluctuates. And in this theory, the main contribution to the width comes from the quantum fluctuations of these Nambu-Goldstone bosons. So these Nambu-Goldstone bosons are d minus 2 massless scalars. Since they're massless scalars in 1 + 1 dimensions, they have rather large fluctuations. And so we find that, and of course we're assuming that this length r is much larger than these other length scales, 1 over the mass gap or 1 over the square root of the string tension. And in this regime, the width squared, which we can define, say, to be delta x squared of the transverse directions, is given by d minus 2 over 2 pi times the string tension times log of r plus other subleading corrections to this. So that's another universal predictions. And then there are also universal predictions for the scattering amplitudes of the Nambu-Goldstone bosons that again were computed by various people in the audience, and for any other property that you can compute for these long strings. So that's the standard story, and we'll see next when it breaks down and what we can do with that. But first, are there any questions about the standard story?
Where does the log come from in the width?
So the log just comes from the properties of two-dimensional scalars. I mean, so if you just compute in a one-dimensional field theory, the fluctuations are essentially just from the propagator of two-dimensional, of massless scalars in 1 + 1 dimensions. That just gives log essentially. So this is a standard computation.
Maybe another question regarding
Yes.
the width. Did you have to specify that the string should be open to talk about the width? Like width of closed string works differently?
Well, if we talk about a closed string, then in principle its wave function would just continue spreading indefinitely in the transverse dimensions. So there's not really a well-defined width. I mean, so I really need to sort of hold its ends if I want to have a finite width. Otherwise, since it's a scalar in 1 + 1 dimensions, its wave function just continues spreading indefinitely. So, I could also take a long string, a closed string, and just fix one of its points or something like that, and then I would get a similar result. But yeah, if I don't fix any point on the string, then it would just continue spreading and spreading, and its wave function would just continue spreading. So for that reason, it's easier to talk about open strings whose ends are fixed, and then we get a finite expression for the width. Any other questions? Okay, So usually we expect that this effective string theory should break down, again, if we get either to the energy of the gap, because in that case, of course, these Navier-Stokes bosons start interacting also with the bulk modes, or to the scale of the square root of the tension, where again, we generally expect extra modes living on the string, which generically do appear. Now, in many theories, and in particular, say in pure Young-Mills theories, then these two scales, the scale of the mass gap and the scale of the string tension, are of the same order of magnitude. In Young-Mills theory, in 4 dimensions, they're of order 1 to QCD, or in 3 dimensions, they're just of order the gauge coupling squared. So in many theories, those scales are of the same order, and the effective string theory is valid up to both of these scales, which are more or less the same. However, interestingly, there are many theories, and in particular QED3, which will be the main topic today, where the mass gap in the bulk is actually much lighter than the square root of the string tension. Now, at first, this seems strange. I mean, if we have a theory that only has one scale, then of course we would expect these two scales to be of the same order. But in fact, there is a generic class of theories in which the scale of the mass gap is much lighter than the scale set by the string tension. And the class where this happens is in theories which are weakly coupled at the scale m gapped. So if we have a field theory that's weakly coupled at the scale m gap, and if the string is a solitonic string of that theory, so it can be written as some classical solution in that weakly coupled theory. So in that circumstance, it's actually very natural for the mass gap to be much lighter than the square root of the string tension, because if we have some weakly coupled theory characterized by the scale in the Lagrangian, then I mean, the mass gap would just be of order 1 in the coupling. It would be independent of the coupling. It would be just the mass of these weakly coupled fields that we have. Well, the tension, since it's given by some classical solution, would typically go like 1 over g squared if g is some coupling constant in this field theory. And then if the theory is weakly coupled, we would naturally find that indeed the mass gap is much below the square root of the string tension. So, so this behavior, even though it's it seems it may seem a bit strange, is actually happens in this very wide class of theories. And this class of theories includes many examples. It includes, say, the abelian Higgs model in 3+1 dimensions, where we have Abrikosov-Nielsen-Olsen strings, which are solitonic strings of that theory. And it also happens in 3 dimensions, where we have strings as domain walls. So one example of this is, say, ANO strings in 3+1 dimensions. And another example is, say, domain walls in phi to the 4th theory. So if we look at lambda phi to the 4th theory in 2+1 dimensions, and so this theory has some potential like this, and if the two vacua are degenerate, then we have a domain wall between them that behaves like a string in 1+1 dimensions, and for appropriate values of the coupling compared to the mass of the scalars, this theory would be weakly coupled, and this domain wall would be a classical solution, and then again we would get this behavior that the mass gap is much lighter than the square root of the string tension. And as I'll remind you in a few minutes, QED in 3 dimensions is also in this class of theories that are weakly coupled at low energies, and where the string can be thought of as a solitonic string. So it also has this property that m gap is much lighter than square root of t.
Do you know, hi Ofer. Yeah, do you know examples in 3 or 4 dimensions where it's the other way around? There is still string
I doubt if
tension,
it's
but
possible to be the other
small.
way around. I mean, it seems very unlikely to have. Yeah, I don't know any example where the mass gap is much above the string tension. It seems very unlikely to me, but yeah, I don't know. Maybe there is some example, but I mean that would sort of require that closed strings don't have any excitations in some sense. I mean, so it's certainly not a generic property.
In 1+1 dimensions, it's of course this adjoint QCD has this.
Yeah, in 2 dimensions, of course, it's different when the string. But yeah, but above 2 dimensions, I doubt if there are any examples of that type. But okay, if somebody knows an example, I'd be happy to hear of it. But yeah, I doubt if there are any examples.
Okay.
So in 4D, is there another interesting class of examples furnished by 4D adjoint QCD with light fermions? Because there I would expect, at least for a small enough,
Right.
And
I mean, there's certainly other examples. Yeah, there are other examples of this behavior. For instance, if we have just QCD with massless fermions, of course we have pions in the bulk. I mean, and again, the pions would be much lighter than the string tension, but I mean, but then of course the string also would not be stable usually. I mean, and yeah,
but in
example with adjoint, in examples with a small enough number of adjoint fermions, then indeed we would also have the analogs of pions that would be massless particles in the bulk, and of course they'd be much lighter than the square root of the string tension. So yes, definitely. There are also other examples, but in those examples I don't think. So yeah, so in those examples this happens for other reasons. I mean, because we have Navier-Stokes bosons that are light because they're Navier-Stokes bosons.
Right.
And maybe there are also other possibilities, but yeah, but the class of theories I'll be talking about today is this class where the theory is weakly coupled. So in this class where the theory is weakly coupled, the usual effective string theory breaks down already when we get to the scale M gap, which is much below the scale of the square root of the string tension. But in this class, we can perform computations also when the energy is of order M gap, just because the theory is weakly coupled at that scale. I mean, so even though the usual effective string theory breaks down, we still just have a weakly coupled field theory, so we can just compute anything we want. And in particular, we can compute all the way up to the scale of the string tension. So at the scale of the string tension, the theory generally does become strongly coupled. I mean, and there we cannot compute anymore. But in these theories, we can still compute all the way up to the scale of the string tension. So, I mean, as a function of energy, we have the usual effective string theory, which is valid up to the scale M gap. But then all the way up to the scale square root T, we can still use just the weakly coupled field theory. Of course, that also captures this regime. We can use the weakly coupled field theory to perform computations of anything we want, and in particular the energy levels, the width, and so on, all the way up to the scale of the square root of the spring tension. So that's what happens in this class of theory. I don't think it happens in these other classes that Alexei mentioned, but at least in this class of theories, we can extend the effective string theory to be valid all the way up to the square root of the string tension. Of course, one problem is that this extension is not universal. I mean, it depends on exactly which weakly coupled field theory we have. So unlike the effective string theory, which is completely universal and that doesn't care at all about which field theory we have, the extension to the scale M gap and beyond does depend on exactly which weakly coupled field theory we have, and we will get different answers in different theories. So I'll focus today on the specific example of QED3, but one can perform similar computations in other examples and see what is the extension of the effective string theory in each of these cases. So that's the general story, and from now on I want to see how it works in the specific case of QED in 2+1 dimensions, but before that, are there any questions about the general story? Okay, so if not, then let's discuss one of the most interesting cases, which is just a QED in 2+1 dimensions. So we just have the usual Lagrangian for QED, where I'll denote the electron mass by ME. And the regime that's going to be interesting for this talk is the regime where the electron mass is very large. We can even take it to go all the way up to infinity, because we want our confining strings to be approximately stable. Of course, if the electrons are light, then the strings can break. But when the electron mass is heavy, then we do have approximately massless. We do have approximately stable strings. Now, in this case, when the electron is heavy, then the only light degree of freedom is the photon, so below the scale of the energy mass. Naively, we just have a theory of free photons. And since we're in 2+1 dimensions, we can also dualize the photon to a scalar field. So we can define a scalar field in the usual way by E times epsilon mu rho d rho phi being equal to F mu nu. So this defines a scalar field phi, where I normalized it such that its kinetic term is the canonical kinetic term. And the scalar phi is periodic because of flux quantization. So we get a scalar field which is periodic with a period E. E has dimensions of square root of mass. It also scalar fields with canonical kinetic terms. And 2+1 dimensions have dimensions of square root mass. So this type of relation makes sense. So naively, when I look at this theory, then at low energies, we just have a massless scalar field whose moduli space is just a circle of circumference r. So we are in 2 + 1 dimensions. The field does have an expectation value, and naively it can just sit at any point on this circle, and we just get a massless scalar field. So that's the naive story. But the full story, as described by Polyakov many years ago, depends on precisely which UV completion we take for this QED theory. So it turns out that in some UV completions, and in particular, if we really take the action to be this QED action all the way up to arbitrarily high energies in the continuum, then there is what's called the topological U1 symmetry, which is an exact global symmetry. So we can define a current epsilon mu nu rho f nu rho, and in QED itself, at least well, classically and also in the quantum theory in some UV completions, this current is obviously exactly conserved. I mean, since f nu rho is just a d nu a rho minus d rho a nu. So we have an exact U1 global symmetry, and if we write this current in terms of this scalar field phi, so this current is just e over 2 pi d mu phi. So the symmetry acts on this scalar field by just shifting its value, its value by a constant. So the symmetry, if it's present, it relates all these different points here on this circle. And then if it's present, then it means that the scalar cannot acquire a mass, and it remains exactly massless. So this is what happens for some UV completions. But it turns out that for other UV completions, which are the cases that I'll be discussing here, this symmetry is actually broken. You can see that the expression for d mu j mu is just df essentially. So for the symmetry is broken if we have any configurations. So if you have any configurations where df is non-zero, then the symmetry is broken. And these configurations are configurations that carry a magnetic charge. Now in 2 + 1 dimensions, we don't really have magnetic monopoles, but we can have instanton-like configurations which are localized in 2 + 1 in 3-dimensional Euclidean space, and which carry this magnetic charge. So if we have these, what are sometimes called instanton monopoles in our theory with a finite action, then they have df not equal to 0, and therefore they lead to a breaking of this global symmetry, and then we can also have a potential for this scalar field, and that leads to confinement, as I'll remind you. Now, for which UV completions does this happen? So one interesting UV completion where this happens is just the lattice U1 theory. So if we construct this U1 theory on the lattice, then there are monopole configurations like this, essentially at the lattice scale. I mean, you can have within one lattice block, you can have one of these instanton monopoles. So the global symmetry is not exact. And another UV completion where this happens, as Polyakov discussed in his original paper, is if we have, say, the Georgiev-Glashow model or similar models, where this U1 comes from a non-abelian theory, say from an SU2 theory, which is broken by some vacuum expectation value for an adjoint scalar down to U1. So in that case, we just have the two Polyakov monopole solutions, which in the context of 3 dimensions are just instantonic configurations, and which also have df not equal to 0. So these types of configurations break the U1, and if the theory is weakly coupled at this, either at the lattice scale here or at the scale of the breaking here, then these solutions have a large action. So the breaking of this U1 is suppressed by the minus the action of these instanton monopole configurations. So the symmetry is broken only by a small amount, but it is still broken. And then once the symmetry is broken, if we discuss the effective action of this scalar field, then it can acquire a potential. So if the symmetry is broken, then we can generate terms in the potential for this scalar field that still have to be periodic with period E, because that's an exact symmetry, but which do not have to be invariant under general shifts of the scalar. So in particular, we can generate terms in the potential that would look like cosine of 2 pi n phi over E, for any bigger than 1. And these terms are indeed generated in all these examples, and they're suppressed by, they're generated by n of these instanton monopoles, so they're suppressed by e to the minus n times this instanton action, which again I'm assuming to be much larger than 1. And then again, if we have UV completion of this type, then the effective low energy action for QED3 becomes the kinetic term of the scalar, and then in this limit of large S monopole, the dominant contribution at low energies is just the potential with n equals 1, so the lowest possible term. So what we get is precisely the one-dimensional Simons-Gordon theory, where we have a potential for the scalar field, which is periodic. So beta here is 2 pi over E. So it's the same potential that we had over there. And so here instead of writing it in terms of E, I wrote it in terms of beta. And this m squared is essentially the coefficient of this non-perturbative potential. So m squared is proportional to e to the minus this monopole action, and so it's much lighter than the scale set by the scale of the gauge coupling and the scales involved in this UV completion. So in the limit that we're talking about, this scale is very small, but at that scale, so m squared, it's evident from this action, it's the mass of this scalar field, namely the mass of the photon. So the photon becomes massive at this very light scale. So instead of having a moduli space, we now just have a single vacuum here at the origin at phi equals 0, or equivalently phi equals E, and all the other vacua are lifted. So that's one piece of the story. And then what happens so we have just a single vacuum, but because the configuration space of the scalar field is a circle, then we can have also domain walls where the scalar field goes around the circle as we cross the domain wall, and in particular, it's easy to find a domain wall solution to the action that I wrote down over there. So the solution is just 4 over beta times arctangents of e to the mx. So this solution describes a domain wall that sits at x equals 0, so x is one of the spatial directions, and then here as x goes to minus infinity, phi goes to 0, while as x goes to plus infinity, then the arctangent goes to pi over 2, so phi goes to 2 pi over beta, which is the same as E. So this gives us a classical domain wall solution that interpolates between this vacuum and itself, but by going once around this circle in the configuration space when we go around it. So this is a classical solution of this action, which of course is just the same as the action for the soliton and the sign as the solution for the soliton and the Simons-Gordon theory in 1 + 1 dimensions. And it's easy to compute the tension of this configuration. So this configuration has some fixed energy density. So say if this is the x direction and this is the y direction, then this solution has some fixed energy per unit length in the y direction, which is what we identify with the tension of the string. And the classical tension of this solution turns out to be 8m divided by beta squared. So beta here plays the role of the coupling constant in this action. For instance, the phi to the 4th interactions are proportional to beta squared. And the tension turns out to be 8m over beta squared. And of course, the interesting thing to relate to our previous discussion is that this is much larger than m squared because the mass is much smaller than the scale set by the electric coupling, which means that m beta squared is much smaller than 1. So this is an example where we do have this situation. So m, of course, is the scale of the mass gap here in the bulk, and the scale is much smaller than the scale that's set by the string tension. And then, of course, the final important thing for this review is that the relation between f mu nu and the scalar field, which I remind you is given by f mu nu equals e times epsilon mu nu rho d rho phi, implies that if we have some electric source or a source for an electric field of this type, then as we go around it, phi does not come back to itself, but it comes back to itself shifted by E, which means that electric sources are precisely endpoints for this string, and therefore we can identify this string with a confining string that connects any two electric sources. They can be Wilson lines, or they can be electrons if the electrons are not infinitely heavy. So this solitonic solution describes the confining string in this QED3 theory. So this was just a review of almost 50-year-old things, I think. But are there any questions about this? Okay, so so let me write again the action. So the bottom line is that in this theory, I mean, we do have this confining string, and it's described, even though the original theory was described in terms of gauge fields and electrons and so on. Then in this Lagrange theory, this string can be described just as a solitonic string in this Simons-Gordon model. And in this limit that m beta squared is much less than 1, then this is a weakly coupled theory at the scale m. So we can compute anything that we want using this description. And in particular, we can compute all the properties of these strings, I mean, the energy levels and so on. So if we compute the spectrum of the theory, so of course, if the spectrum, if we have no string, so without a string, then we just have the photon. I mean, and of course, then we have multi-photon states. So we have photon states starting at the scale m. I mean, and then depending on their momentum in space, we can have any energy above the scale m. But if we now look at the spectrum in the presence of a long string, then so in the presence of a long string, so we can have we can just expand the field phi around this long string solution and then compute the spectrum. So we take phi equals phi string plus delta phi, and then we just can compute the spectrum just in the usual way by diagonalizing the quadratic terms for this delta phi. And then we find that the spectrum contains two types of modes. So the spectrum in the presence of the long string has two types of excitations. First of all, there are the photons in the bulk. So of course, when the photons are far away from the string, they don't even feel the string. So far away, the spectrum is not really corrected, but it is modified by some phase shift. I mean, as we scatter one of these scalar fields, say off the string from one side to the other, it does get a phase shift. I mean, so the theory is not oblivious to this string, but this still gives just a continuum of modes starting at the scale m. And then on top of that, in the presence of the string, I mean, obviously on general grounds, we must have also these massless Nambu-Gaussian bosons. So and we find that if we just expand in these small fluctuations around the classical solutions, we do have also the Nambu-Gaussian boson corresponding to the transverse motion of the string, in this case in the y direction, say y is a function of x and t of the string, so that gives us a massless scalar field. And in this case, it turns out that actually these are the only excitations in the spectrum. We only have this massless 1 + 1 dimensional fields, and then this continuum of 2 + 1 dimensional modes. Of course, in other theories, like in the phi to the 4th theory, one finds that there are also additional modes attached to the string, like one can think of them as bound states of the bulk particles with a string. But in this specific case of the Simons-Gordon theory, or QED3, there are no other modes, so the full spectrum is just the Nambu-Gaussian bosons plus, the single Nambu-Gaussian boson plus the excitations of the bulk fields. And then we can just do computations in this theory and see what we get. So I guess that's the end of part 2 of describing how we set up the computation of the effective string theory. So in this case, we at the scale m, instead of using the effective string theory, we can just use this weakly coupled field theory to compute anything that we want, all the way up to the scale of the tension of the string. And then in the last few minutes, I'll describe the results that we find from computations in this weakly coupled field theory. But before that, are there any questions about the setup? Okay, so of course, as I said, we can just compute anything that we want, but let me focus just on two computations which show very specific differences from the usual story of effective string theory. So let me start actually with the second property that I discussed in general for effective string theory, namely the width of the string. So we can discuss the width of the string. So the string, again, we can think of it as a soliton of the scalar field, or we can think of it as just a flux line, of the electric field. So of course it carries some electric flux from one side of the string to the other side. And one way to define the width is just to look at the profile of the electric field. Say we can consider, say, the expectation value of the electric field as a function, say, of the electric field in the y direction as a function of this transverse distance e from the string. So we can define the width by just considering this expectation value or its square and whatever we want, and then just see what's the width of the string. And then the big difference from the usual effective string theory is that in this case, already just in the classical solution that we wrote down up there, then already this string has some width that we can just compute the effective, the profile of this string by just taking that classical solution, plugging it into f mu nu, and then we just get the profile of the electric field. And what we see is that already classically, the electric field and also its expectation value, of course, classically it's the same thing, decays as e to the minus m times x as we move away from the string in either direction. So the classical solution has some width given by 1 over m. I mean, naturally, since that's the only scale in this weakly coupled field theory. And then the profile of the string has this exponential decay going as e to the minus mx as we go to either side of the string. So that's the result that we get just from the classical solution. And then, of course, we have a weakly coupled quantum field theory, so we can compute also the quantum corrections to this. So in particular, we can just compute, say, the one loop correction to this classical result for the width of the string. And then what we find is that, so this classical result gives us a width for an open string, which just goes like essentially 1 over m squared independent of r. The quantum corrections add to this the extra contribution, so the dominant. So if the string is very long, again, if r is much bigger than 1 over m, so I'm assuming here, of course, that the string has a length much bigger than 1 over m, so that I can really trust this classical solution for the string, and I don't have to say exactly what happens at the endpoints. So in that type of configuration, then we have this classical contribution to the width, and then on top of that, we still have the Nambu-Goso bosons, which give the dominant quantum correction, and so they give an extra contribution, which is essentially exactly the same as the contribution that we had just in the usual effective string theory, namely this goes as 1 over 2 pi times the tension times log of r over r0, and if we look, the full profile is essentially a convolution of a Gaussian that has this width with this classical solution that just decays exponentially at the scale 1 over m. Now, the interesting thing is that in the regime that we're talking about, because m squared is much smaller than the string tension, then this classical contribution is actually much larger than the quantum correction, unless the radius is really exponentially large. I mean, so the length of the, so unless the radius is really exponentially large in this parameter, which is of the tension over the mass squared. So for any, and again, this is a very large parameter in the regime that we're talking about. I mean, this is exponentially large in this S monopole that we discussed before. So unless R is exponentially large, then the classical width dominates over this quantum width. So for any reasonably sized string that is not exponentially large, we just find this classical result for the width of the string, and the quantum fluctuations are completely negligible compared to this result. So the claim is that these types of effective strings in weakly coupled field theories, the width behaves completely differently than the width of the usual strings for any length which is not exponentially large. So again, this is valid as long as R is much less than the exponential of T over M squared in whatever units we want. I mean, that's sublating to this exponential piece. So for any reasonable length of the string, this classical width dominates, and therefore that's what we would expect to measure, say, in lattice simulations or in any other context where we measure the width of this string. So
Can I ask a question about this?
Yes. Questions?
So how sensitive is this result to the particular weakly coupled setup that you have versus being just kind of
this result is universal. I mean, so I think any soliton would have a width that's of order 1 over m gap. I mean, just because that's the typical scale of this theory. So we will always have that the classical width goes like 1 over m gap, and this quantum correction is also completely universal, just coming from the Navier-Wilson bosons. Yes, so this behavior is universal in this class of theories that are weakly coupled at the scale m gap. So this does not really depend on any of the details. Yeah, so thanks for mentioning that, indeed.
Okay.
Any other questions about this?
Maybe can I ask, given this classical result, how, like you were at the beginning, you were saying there's an energy scale range in which I'm below the string tension, and there I have a one-dimensional object that looks like a string. But actually, at scales of order 1 over m, like length scales of order 1 over m, already I can see a lot of extension of this object. So if I have some particle which has energy larger than m, but below the square root of this string, it's traveling in a medium which is not really a boundary, like one-dimensional. So how is the effectivity theory affected?
So yeah, so it depends exactly which question you want to ask. So definitely for some questions, I mean, so the classical solution has this width 1 over m, and then obviously if you take a momentum such that you're sensitive to distances smaller than 1 over m, then you will see this classical the non-trivial internal structure of this string. So the string will not behave like a point-like object, and of course that's what is related to all these differences from the usual effective string theory that I'm describing. So definitely above the scale 1 over m, you are sensitive to all these to the internal structure of the string. But I mean, the whole point is that that is one of the reasons why the usual effective string theory breaks it down at this scale. But nevertheless, because this structure is still just governed by a weakly coupled field theory, we can still compute anything that we want. So even well above the scale 1 over m, so the string doesn't look point-like anymore. I mean, it has all its internal structure and so on, but we can still compute anything that we want just in this weakly coupled field theory. But again,
and sorry,
it's obviously going to be different from the effective string theory, which assumes different assumptions.
But it's still fine to consider a two-dimensional field theory coupled to a higher dimensional bulk, even in this range between m and the square root of 2.
Well, sorry. Here I was not talking. I was not. Yeah, sorry.
I guess not here.
I was not talking here in this language of a two-dimensional theory coupled to a three-dimensional bulk. We just have the three-dimensional bulk theory. In the theory, we're expanding around this solitonic solution, but we always have the full 3D theory. I mean, and then in this expansion, this 2D Navier-Wilson boson is just one of the modes that we find in this expansion. So we do have these two-dimensional modes coupled to the three-dimensional modes. But the full weakly coupled theory contains all of these modes. I mean, so it's not that we have two separate theories. It's just that when we expand the three-dimensional theory, we find these two-dimensional modes of the string, and we find the three-dimensional modes. But everything is weakly coupled. I mean, we can just consider all these modes together and compute whatever we want.
Thank you.
Any other questions about the width? Okay, so if not, then I think the last result that I want to present is for the energy levels of the string. So I wrote above here the prediction for the energy levels that we get from the usual standard effective string theory. And in this QED3 theory, we can again take a long string wrapped around a circle and compute its energy levels. I mean, for now, we just computed the ground state, so we can just ask what's the ground state if we take one of these solitonic strings, and again, just wrap it on a circle of circumference L. So of course, in the classical solution, so this is now in this y direction, so we have now some circumference Ly of the circle in the y direction, and we're just putting this solitonic solution on a circle that's wrapped in the y direction. So classically, of course, the energy that we find is just the tension of the string, which I remind you was 8m over beta squared times this length. So that's the classical answer. And then we can just compute what's the one-loop correction to this solution. So we just put in the string, just expand around that solution and compute the expectation value of the energy at one loop order. And we find several different types of corrections at one loop order in this weakly coupled field theory. One correction, well, let me maybe write down all the corrections first that we find at one loop order. So the full result at one loop order takes this form. And then there are two loop and higher orders that start going as 1 over the tension. I mean, so here the tree level goes like the tension, the next order is of order tension to the 0, and then the next order corrections in this weakly coupled expansion go like 1 over the tension. So the one loop contributions are all independent of the tension, and we see that we have 3 different types of terms here in the one loop correction that we compute from this field theory. So the first term that we find, so this term is proportional to Ly, so this is just a correction to the string tension. Of course, there's nothing here that protects the tension. So we see that the tension gets a correction that's proportional to m squared, which again is much smaller than t in this weakly coupled regime, so that's consistent. So that's one term that we find at one loop. The second term that we find, minus pi over 6 times Ly, is the famous Wilshire term that comes from essentially the Casimir energy of this massless scalar, the Navier-Stokes boson living on a circle. And this term is also the term that we would find if we just take this universal formula for effective string theory. So of course, the effective string theory should be valid in the regime. So for Ly, which is much bigger than the scale of the mass gap, then we should reproduce the effective string theory result. Now here we have this polylogarithm function of e to the minus m times Ly, and if Ly is much bigger than 1 over m, then this is very small, so this contribution is negligible. So in that limit, we just get this Tly minus pi over 6 Ly, and that's exactly the same as what we get by expanding this Navier-Stokes formula that's written up there. So in this limit, we do agree with the usual effective string theory, as we have to, and these extra corrections are small. But what we see is that when Ly becomes of order 1 over n, then this function becomes non-trivial, so we have here this polylogarithm function, and it does give us large corrections to the ground state energy of this string, but these corrections are still controllable. So this term is important once Ly is of order 1 over m, and again, it can go all the way to, and in principle, it's going to go all the way to 1 over square root of the string tension. But so in this regime where Ly is of order 1 over m, or all the way down to 1 over the square root of the string tension, this gives us the leading correction to the usual effective string theory, and this correction is definitely not negligible. And just recently, there was a paper by Casella and Mariani where they looked for this correction in QED3 on the lattice, and they found some indications that indeed this correction to the ground state energy is there. Now this part is not expected to be universal. I mean, so this Wilshire term is going to be universal. This correction to the string tension is presumably not universal. I mean, in any theory of this type, you would expect some correction, but the coefficient is definitely not universal. And here, I think even the functional form of this, there's no reason why it should be universal. This just happens to be the form that we find for QED3, but in other theories, presumably, we would find different corrections of this order. But again, the important thing is that we can't compute it, and there is a well-defined prediction for this correction to the ground state energy, even in this regime where the usual effective string theory breaks down. So any questions about the ground state energy of these long strings? So again, the string is still long compared to the scale 1 over square root t, but it does not have to be long compared to 1 over m for this formula to be valid.
You may be about to talk about this, but is there a way to build some effective field theory description of this where you just have an EFT with more than one scale, basically, more than one UV scale?
Well, I mean, in some sense, that EFT is just this weakly coupled theory of the field phi. I mean, that does give us a completely weakly coupled description that, again, includes the Navier-Stokes boson, it includes the bulk photon, and it includes everything up to the scale of the string tension. I mean, it's weakly coupled up to the scale of the string tension, and it describes the physics there well. So I don't think we really need any other description. I mean, that description already has everything in it.
Yeah, that's a particular example of it, but I mean,
No, but I think, again, in any theory of this type that will be weakly coupled, I mean, and where the weak coupling is what explains the large ratio between the mass gap in the bulk and the string tension, then this will be the generic behavior that after the scale-up gap, you have the usual effective string theory, but then above that, you need to include also the bulk modes, but they are all described just by weakly coupled field theory. And again, for theories, it will be a different weakly coupled field theory, but that is always going to be a good description up to the scale of the string tension, where that theory becomes strongly coupled, and there you need to do something else.
Okay, thank you.
So yeah, so this is the other result. Now, I mean, we did also compute scattering amplitudes, but I mean, I think they're not too interesting. I mean, so obviously, if we look at the scattering amplitudes of the Navier-Stokes bosons, then once you have enough energy, so if the energy is above the mass gap, then they can start scattering also to these bulk fields. I mean, so you can create these bulk photons when you have enough energy for it, and you can just compute. So we computed some tree-level scattering amplitudes. So that again, so the details are not too interesting. So again, I don't expect them to be universal, but there are very specific corrections to the effective string theory that one can compute here in the context of these weakly coupled field theories. So let me just summarize. I mean, so the main summary is that in theories of this type, even though the usual effective string theory breaks down at the scale-M gap, then we do still have this other weakly coupled description that's valid all the way up to the scale square root t, and in particular, that's the case in QED3. So in these cases, we do have this generalization of effective string theory, which is not universal, but it is predictive, and which allows us to still make predictions all the way up to the scale of the string tension. So thank you. Any more questions?
I wanted to ask you, because okay, you didn't talk much about it, but in the paper you discussed the scattering in more details, and you found some infrared divergences.
Yes.
I was wondering if you have some understanding by now. What
Yeah, so that's something that we're still working on. I mean, so in particular, my student Nathaniel is still working on that. So in the paper, when we did these computations, so we did it in a specific setup, and then so when we have scattering of Navier-Stokes bosons, say, to form these bulk photons, then in some cases, the momentum in the transverse direction is conserved, while in other cases, say, we can just create some bulk photon that will carry some momentum, and then the string itself recoils and absorbs some of that momentum. Of course, in the full theory, the momentum is always conserved. I mean, so if we emit some bulk photon with some momentum, then the string has to recoil with an opposite momentum. And that we did not properly take into account in our computations. So I think that the computations had in our paper were correct in the case where the string doesn't recoil, but they were not exactly precise in the case where the string recoiled, and that's what led to some divergences that we found. So we're now working on fixing that, so we still don't have complete results, but we hope that when we take the recoil correctly into account, we will find consistent answers also for
by
these
recoil of the string, do you have in mind something like including the, in a sense, zero mode of the Goldstone boson as an actual degree of freedom? Because again, usually the zero mode of Goldstone boson we don't include, and for fundamental strings we include them, right? Because the constant and linear momentum, I mean, we can include as a target space momentum. So you say here you need to include some mode like this, and that
yes. Right, exactly. So that mode is the mode that I mean, of course, the full momentum is conserved, I mean, in the full theory. So if we emit some particles with some momentum, the string has to recoil, and that is precisely absorbed by that zero mode. And then we had these infrared divergences because we did not properly quantize that zero mode. But we believe that when we do properly take it into account, we will get reasonable answers, but that's still a work in progress.
Question. This log R over R naught, just for the usual pure glue theory, has it been measured on the lattice? Has it been observed?
Yeah, pretty sure it was measured. I mean, of course, there are a lot of experts in the audience, so I'll leave them to answer it. But yeah.
So you need pretty long string to see this fattening in the middle or something.
No, I don't think very long. I mean, just a few times the QCD scale should already be enough to see it.
Okay.
But maybe the less people can.
Yeah, in these famous movies where you see the string being stretched back and forth, it's not too visible.
Yeah, no, okay, yeah, this is for a static string. I mean, this log, I mean, yeah, of course, when the string is dynamical, it's a different story.
I mean, it's a movie.
The log I was talking about was for a static string. If you just hold its ends and then it just fluctuates back and forth here, and then you should see.
I mean, it's just a movie made of different sizes of the string together. Yeah.
Right.
Yeah, I mean, it's not very visible that it gets a little fatter in the middle.
Mm-hmm. Yeah, but anyway, I mean, it's a trivial computation to see it, and I assume that in the lattice it can also be found.
Are not in this case is basically string thickness, the basic QCD scale or something.
Mm-hmm.
Yeah. So what is R naught in your case? R naught was M.
Well, it's not really well defined. It depends how you define your other terms. Yeah, it could be M or the scale of the string tension. It doesn't really matter for what I discussed. But yeah, I guess the scale of the string tension.
It's the renormalization of the classical piece, right?
Yeah, it would naturally be the string tension, but I think it would be the string tension. But okay, it doesn't.
If I can add a comment, I don't know if you hear me.
Yes.
If I can add a comment, this R naught scale is called in the lattice community intrinsic width. And if you evaluate it, it behaves exactly as Ofer is saying, is exponentially decreasing term in the width. And the scale of the exponential is exactly the inverse of the global mass, the lowest global mass, which is the lowest scale in the bulk. So it is exactly the same pattern that you see here, but in the QED case that Ofer was describing, this mass scale is much lower. So what you see is that this exponential behavior is much, much wider, and the string behaves in a completely different way, but the reason is exactly that.
So in that case, you basically can't see the log.
Maybe I should just stress that it's very difficult to see all these properties on the lattice because all these properties depend on the separation of scales between the scale and gap, the scale of square root t, and then if we're doing lattice simulations, then we also have the lattice scale somewhere, and we want all these scales to be very separated from each other to have this type of behavior, and obviously that's very challenging on the lattice. So of course it requires heroic efforts by the lattice people to really be able to see these things, but it seems like they are able to.
Yeah. What helps you in the QD case is that you have duality, which allows you to perform simulations in the dual setting, and so you can. So to speak, avoid the signal to noise ratio decreasing exponentially. And so this allows you to reach very large distances between the two sources. Yeah. So by the way, Ofer, it was a wonderful talk.
Ofer, I think that much of what you did could also be done for 4D adjoint QCD with two flavors, because there, the long distance theory, if there's chiral symmetry breaking, is a CP1 sigma model.
Yes.
And that thing will have solitonic strings because pi 2 of CP1 is Z, so there will be solitonic strings.
Okay.
Good. And one should be able to repeat your analysis. And I think actually, in fact, it would be quite interesting because it's a really 4D.
I say that those solitonic strings are the same as the confining strings in the.
They're supposed to be, yes, they're supposed to. So one can study them.
Right. Okay.
People may have even done it for other reasons in the past, but
okay, great. So that is definitely another example where this type of analysis should be possible. Indeed, I mean there may be some differences because of course the mass gap in the bulk is 0, so there may be some subtleties in that case, which.
Well, you could add a small. You could add. I mean, that's actually one of the things.
Break explicitly the chiral symmetry.
Yeah, you could add a small quark mass, right? And then it should parallel this quite closely.
Right. Yeah, but it may be interesting to see what happens when you actually take it to 0 and then.
Yeah, absolutely. I think that's something that in this context is hard to do because you also kill the string tension in that. But in that other 4D example, that wouldn't happen. I think it's quite a well-motivated thing to study. Yeah.
What is the string tension in that case? Could you remind?
Lambda QCD. I mean, that's the expectation.
Yeah, so that is just lambda QCD.
I mean, that also sets the width of the solitonic string. I mean, it's set by this higher correction span. It's like a skirm term in this nonlinear sigma model, or.
Yeah, I don't know. I haven't studied it. To be honest, I never thought of pursuing this until your talk at all. So I haven't thought it through. But
because
maybe the width of the string would diverge when you take the mass to 0.
Here, the width of the string is much longer than kind of the string scale, right? Than the string tension.
Yeah, that's true in all these examples, definitely.
I think that should also be true.
That's the example. What there is only one scale. There is lambda QCD. So then, then there the string width